Hey folks, welcome to this week's video. I'm having some technical difficulties, so this video will look slightly different from the others. But let's get going. My goals for you today are up here. And let's dive right in and answer one of these questions. And then we'll back up and look at the steps we took to do it. So the question here, as you can see, we've got a radar gun, a speed trap, 30 feet away from the road. The radar sees your car approaching at 80 feet per second. This isn't the speed on the road. This is how the distance between the actual radar detector and the car is closing. And that's at the moment when the car is 50 feet from the gun. Again, diagonally, not on the road. So the question is, if the speed limit is 65 miles per hour, are you speeding? So we'll start this question and all these questions with a picture. Maybe we can draw the road. We can put the mile marker here, and I stashed some pictures here that I can use for our setup. And then let's add in some of the important distances and things. So we know that the trap is 30 feet from the side of the road. Maybe I drew that line a little bit too long. We know we'll want to talk about the distance between the radar gun and the car. And, well, we can talk about this distance too, which in fact is, we could say, is the distance to the mile marker. So we get a right triangle out of this picture. And so to say that the radar sees our car approaching at 80 feet per second means that this hypotenuse is shrinking at 80 feet per second. When your car is 50 feet from the radar gun means when the hypotenuse is 50 feet long, it's shrinking at a rate of 80 feet per second. So this will get a lot easier once we name some of these variables that we'll talk about. Maybe let's let D, big D, be the distance between the car and the radar. So we can put that picture, or put that right in the picture, and we'll let, I don't know, little x be the distance from the car to the mile marker. And these are variables, that is, things that are changing. I don't need to give a variable name to 30 because, well, that's not changing. The speed trap is set up 30 feet from the edge of the road. But while we're here, everything is dependent on time. So let's think about our corresponding rates. If we could talk about D, capital D, the distance between the car and the radar, we could talk about dt, the rate at which that's changing, and we can also talk about dx dt. So again, dt is how the hypotenuse is shrinking, dx dt is how this horizontal leg is shrinking. And then what I'd like to do next is think about, well, what else do we know? There are some numbers in here. Let's see. The radar sees your car approaching at 80 feet per second when your car is 50 feet from the radar gun. So at some moment, this big capital D is going to be 50 feet. And at the same moment, d dt, the rate at which the hypotenuse is changing, will be minus 80. And it's minus because, well, this is shrinking. We're not given x, and we're not given dx dt. In fact, the question, are you speeding, is really a question about the change in x. Right, we want to know how quickly this is shrinking. So in fact, this is our answer. We want this. So how do we do it? Well, in order to talk about these rates, we first need an equation for which we can take the derivative. So we want an equation that relates d and x. Well, this is a right triangle, and these are sides of that right triangle. So the one thing that should come to mind is the Pythagorean theorem. We should get that d squared, the hypotenuse squared, is 30 squared plus x squared. Maybe I'll redraw the picture here, just so you have it in your mind. And then we can take the derivative of both sides with respect to t, because time is our independent variable here. We can't forget to use the chain rule to use the ideas of implicit differentiation. So we'll have 2 times d, that's the power rule, but then sort of the derivative of the inside function, derivative of d is d dt. 30 squared, well, the derivative of that is just 0. And x squared, its derivative is 2x times dx dt. Now, we have a value to plug in for d dt, that was this minus 80. We have a value to plug in for d, that was this 50. Dx dt is the thing we want, but then you'll notice there's one piece that we can't plug in yet. Well, I think we can actually. Our triangle looks like this. We know that d is 50 at the moment in question, so it's not always 50, it's changing as the car moves. This leg is 30, that was just given to us. And we can ask at that moment, what's x? Well, maybe you recognize this as a 3, 4, 5 triangle, so it's 40. And if not, we can say, well, we know 50 squared is equal to 30 squared plus x squared. You can do the math and see that x has to be 40. So then we've got everything we need. After we took the derivative, we can plug in what we know. That we said d was 50, that was given to us. We said that d dt was minus 80. We just found that x was 40. And our dx dt, well, that's the thing we want. That's the thing we want to solve for. So let's see what we've got. On the left-hand side, 2 times 50 is 100, times minus 80 is minus 8,000. 2 times 40 is 80. We can divide both sides by that and see that dx dt is minus 100. So knowing a value for d dt, we found that dx dt minus 100, that is, this leg of the triangle is shrinking at 100 feet per second. Or another way to say that is this car is moving to the left at 100 feet per second. Well, if the speed limit is about 95 feet per second, then the answer is yes, we're speeding by about 5 feet per second. Oops. I don't know how that translates into miles per hour. But let's back up and let's sort of enumerate the steps here. So this question maybe looked intimidating. Hopefully, looking back, you understand the steps that I took, but let's give them all names. So the very first step was draw a picture. Most of these problems have a geometric aspect to them. We want to be able to use that. So we'll start by drawing a picture. Step 2 was to name everything. We'll name the quantities. And when I say quantities, I mean variables, things that are changing. We didn't need to give a name to the 30 because, well, it's constant, it's stuck at 30. And once we name those quantities, we have to think about their rates. Now, we don't really have a choice. If we name the distance d, then its rate is d dt. Step 3 was to sort of take inventory. That is, we looked at these quantities we named, d and x. We looked at these rates that came along with them, and we asked, well, which of them do we know? Well, right in the question, this 50 feet and this 80 feet per second, those were in there. So we made sure we know where those go in our list of quantities and rates. And then also, just as important, we thought about what we don't know and we need to know to answer the question. Our next step was to relate the quantities. We related d and x by using the Pythagorean theorem in this case. It won't always be the Pythagorean theorem. It'll be some other way, perhaps. And then the next step, so we didn't plug anything in yet. The next step was to use implicit differentiation. So that is differentiate with respect to t. So use implicit differentiation. And we don't forget the chain rule. Right, the chain rule is what told us that when we apply the power rule here, we had to also multiply by the derivative of d, sort of the inside function, to the square. And only after we differentiated, and this is the same as implicit differentiation, only after differentiating did we plug in the values. So we plugged in the known values. We knew d, we knew dt, dt. We needed to solve for x. Let's say using geometry. And then solve. For almost all these questions, the unknown is going to be a rate. So that's how we approach this. So you can review my work, and in the next video, we'll do one more example.